Hi everybody, Dr. Jensen. We're here for part 2, Data Management and Cleaning for CCJ 3701, Research Methods in Criminology. You may notice I'm talking a little faster because I figure you can read and hear a little bit quicker than than I can talk. So I'll be talking a little faster, but feel free to pause me or skip ahead, move back. I won't be offended. I won't even know. So remember, as we left off, we were talking about this chart, the histogram, and this was basically just a graphical representation of a variable called children's age reported by caregiver. So we saw data that was kind of all over the place. If you know your topic and your data, this is not concerning at all. So remember, often young children's ages are recorded in months, 6 months, 12 months, 18 months, and you're going to see little spikes at 12, 18, 24, 30, 36, because people tend to remember those milestone months. A 36-month-old is a 3-year-old, a 24-month-old is a 2-year-old, and sometimes that's all they can remember. They don't maybe keep track of the months as well. So this is not concerning at all. This is actually very normal data. It looks funny on the histogram, but if you know your population and you know your topic, not cause for concern. This is what we would call a logic check. So here you have 3 frequencies presented on your screen. You have sex, pregnancy status, and age. So let's just walk through the output of a frequency quick if you are foggy on it. So the very leftmost part of any frequency is always going to be the topic and the responses that were provided. So here we have sex, 0 and 1, female, male, pregnancy status, 0 and 1, yes, no, age, and these are the raw ages, an 11-year-old, 23-year-old, 29-year-old, so forth. The frequency column is the actual count of how many people gave that response. So here we have 4 females, 3 males, 3 no's, 4 yeses, 1 11-year-old, 1 23-year-old, 1 29-year-old, and so forth. Percent actually just shows you the proportion of that response that makes up the total. The cumulative frequency is how that response adds up to a total count. Okay, so we have 4 females rounding up to out of a total of 7 people altogether. Cumulative percent is very similar, where we actually add those proportions together eventually to the total 100%. Okay, so that's just a little refresher on reading a frequency. But let's say we wanted to look at 2 variables, sex and pregnancy status, and we ran a cross tab, which actually shows us those 2 together in a little 2x2 table. So here we have across the column pregnancy status, yes, no, and across the rows we have sex, male or female. So here we could read across and say, okay, female, 1 female said, no, I am not pregnant. 3 females said, yes, I am pregnant, for a total of 4. Okay, and then across the bottom, 2 males said, no, I'm not pregnant. 1 male said, yes, I am pregnant, for a total of 3. We got a problem. We know it is humanly impossible for a male to say, yes, I'm pregnant. So here we clearly have an error. Maybe something was punched in wrong when data was recorded. So this is that logic check. Is this even making sense, right? Pregnant male. No, we shouldn't get a response of yes for someone that said they're male. We know we have an error, so now we got to go fix it. So again, this is just using good logic, common sense. Is what I see what I should be seeing? Another way to detect errors is associations. So this is where we examine a known or expected relationship between 2 variables, where the literature review or your wonderment or you're jumping into the journals and the research on it, getting to know your topic, that's going to help you with this. Most helpful when a very consistent relationship is known to exist or there is good reason to expect one. So here's an example from criminology. You've probably been taught that there's an age-crime relationship, that as people age, they generally offend more up until about age 17 and a half. That's peak offending age. And then it drops off sharply after about age 24. So we know that that relationship is strong and very consistent, so we should expect to see that in data that we have on people's offending and how old they are. So if they told me I'm 12 years old, I would predict that their offending would be much lower than if they told me they were 19. Okay? So that's when you just know your topic. You know what tends to happen in that research. Here's another example, height and weight. Biology is full of really great relationships. So height and weight are highly correlated. This is actually an output of a correlation coefficient, which we will run later in this class. So you see these 2 corners that have perfect 1s in them for height and weight. That tells me there is a perfect positive relationship, that generally as people increase in their height, they also increase in their weight. And knowing someone's height, I can become really good at estimating their weight, and vice versa, that there's some kind of consistent relationship between those 2. However, if we were to run and plot out all the little points of data, all the little heights, all the little weights, and stick it in a graph, and this is called a scatter plot, and we got this funky looking shotgun pattern, that would be a red flag. You'd go, hey, I should have a beautiful line where all these dots line up really nicely in this positive relationship. I shouldn't have this big old mess on the screen. That would be really bad. So again, graphing, checking for relationships, seeing what's going on there, it's going to give away problems in your data. Okay, so again, it's not enough to simply identify the errors. You also have to correct them. So these are some ways you can do that. So first, set it to missing values, exclude it from the analysis. Or two, don't use a poorly measured variable, just simply move on to something else. And three, impute values into the missing data, replace it with something else. So I'll show you some examples. So remember that question that we had those funky negative values inside all these satisfaction levels people reported based off of this question here. So they were supposed to say excellent, very good, fair, or poor, rating their representative. But we got output that looked like this, and we got a mean that looked like that. Okay, so where we see a 0.461 for the mean, and then the median and mode are 4s. That again is a red flag. Those should all be about the same value. So it's very clear to us that they're actually calculating, SPSS is calculating that -8 into the mean as an actual -8 rather than representing a response of I don't know or skip or a non-response. So to change it to missing data, we would do something like this. So now those responses have been removed, and the only ones that are left are the valid responses. Okay, and now we run a new mean, median, and mode, and we can see, aha, we have mostly 4s. So now we know those are normal data, they're normally distributed, those are lining up really nice. We did not actually delete those -8s and 9s, we simply told SPSS to ignore them and exclude them from the analysis. That's all it is. We almost never delete data. We can always work around bad data, okay? So setting the errors or the values outside the valid range or the broken ones, or non-responses like -999 to missing means that those observations will not be used in your statistic. This works well in situations with relatively few errors where we can just set those aside. Because it would be a shame to throw away an entire survey just because they gave an answer of an I don't know on one question, right? They may have good answers across a lot of other questions, but they happen to not know the answer to one. So we want to keep all the good data and just exclude the data that doesn't work. That's really all it is when you set it to missing. We just call it missing data because we can't really analyze it. How would you analyze a response of I don't know? You can't. Okay? Error correction. This is not technically a correction measure, but sometimes we just have to move on. We have to exclude a variable that's broken, it doesn't work, there's just too many problems with it, and just keep in mind it is not true that any data are better than no data. Garbage in, garbage out. We don't want to analyze stuff that's broken because we're going to get a result that's inaccurate. Okay? Sometimes it comes from bad question writing. So look at this question from a survey that I actually saw. Question 19, what is your current age in years? Circle one category. 17 to 20, 21 to 25, 26 to 29. Well, here's a problem. What if I'm 20 and a half, about to turn 21? Do I put that I'm 21 or do I put that I'm 20? So you may have people that are falling between these categories that aren't going to be represented very well, or you're going to force them to make a category that might not be as accurate. And what about people that are younger than 17 and people that are older than 29? They don't even have a category to choose from, so they've been kind of excluded. So sometimes you get questions like this that are just poorly worded, or the categories that they gave as response choices are bad. It's typical to see this sometimes. Everyone thinks they know how to write a survey. I got a question like this from a city survey once. It was asking new residents, why did you move to the city? The primary reason for moving to the city, was it because of the jobs or because of the quality of life? Yes or no? I went, okay, if I say yes, they're not going to know which one I was responding to. How would they even interpret that? That's called a double-barreled question, and people do that kind of stuff all the time in surveys. And it's garbage. I mean, you can't analyze a response of yes or no because you don't know what they're responding yes or no to. Sometimes we don't include enough categories of responses to involve everybody. So this kind of stuff happens. So just keep in mind, sometimes it's just bad data and you have to just move on and find something else that'll work. Data imputation, this is one of the last things you can do, is just simply replace the bad data with something else that's more accurate. You substitute some value, maybe like the average or the mean, over the missing or the error value. Okay, so for example, we were working on a survey on campus, that had drinking behaviors for students, and for some dumb reason we forgot to ask students what their age was. We did also ask them what year they were in school, freshman, sophomore, junior, senior, but we didn't ask their age. Age would be kind of important to ask in drinking behaviors, so what we did instead is we calculated what a typical age would be for a freshman, a sophomore, or a junior, and we imputed that into the data. So it was our best estimate. We didn't do a lot of analysis with that variable because it's still highly inaccurate, right? You're going to have older freshmen, younger seniors, and vice versa. So when you don't have the data in that kind of way, it might just be better to move on. But occasionally you just have to make an estimate and replace it and do your very best imputation you can. I don't recommend this. I usually never do stuff like this unless it's a dire circumstance. Another thing to do that's just going to help you with data analysis is simply to use clean data. So we have data from government sources, from universities and research centers that have large teams of people that are highly trained, that do quality checks, and then release publicly available data sets, just like AdHealth, to people to use. So these are good, clean data. Occasionally they still will have some errors here and there, but these types of groups are very good at sending out updates and notifications if they see any problems, and then sending out replacements or clean data sets if they do see anything. So CDC, Centers for Disease Control, national surveys and studies, AdHealth is one of those, the General Social Survey, the Bureau of Justice Statistics, which calculates a lot of research on FBI data like the Uniform Crime Report or NIBRS or the victimization surveys. They report to the Department of Justice. So you actually have a lot of different places you can get clean data. Okay, one other thing to note before we wrap up is when you're moving data from one system to another or one kind of software to another, these are some things you want to keep in mind. So maybe your boss gives you data in Excel or it's in a CSV format, comma separated values. That can actually be read by SPSS, and maybe you want to dump it into SPSS so you can analyze it a little better. Before you do that, you want to kind of do these checks. So when importing or exporting data from one system to another, always check the data before and after. Did you get all the content of the first and the last record, get all the cases, or did any get cut off? Is the total number of records the same? Is the frequency table of the first and the last field of a variable the same? How about the date ranges? Are they the same before and after? Be careful of how those missing values or negative values are handled. And those long numerical values like social security numbers or dates, sometimes they get turned into funny looking text, lop off leading zeros, and those kind of things. So you just want to make sure that your data comes in cleanly. And this happens all the time. So these are my data commandments, my good data management practices, and these are things you're going to find yourself doing as you're working on your labs and your final research projects. So you might want to pause and jot these down so you can start developing these habits. Number 1, use syntax. We're going to be showing you how to run syntax or just writing the raw script or commands for how to do a function in SPSS. It's kind of like writing HTML code, but it's a record you can save of all the stuff you did. And you can put your notes in it. Number 2, use comments in syntax. So you can tell yourself, this is what this means, or this is what I was doing. Make good naming conventions for files and variables. Use good version control. So if you're in a data set one day and not the other, you don't forget stuff. Save your log files or your output files. Separate analysis from your data manipulation. So keep extra copies of your data sets so you have an original that's clean in case you mess up on something. Keep a good data diary. All 600 students that I've taught will tell you they had a spiral-bound notebook that they could jot down stuff with a pencil and actually make sure they're using the right variable and keeping track of the information in there, any changes they made to it. It's just a good practice in recoding. Back up your files often. Number 8, never recode into the same variable. That's overwriting the variable like save as. Run a sanity check or a logic check on anything you build, pull apart, or shove together. Run those descriptive statistics before every analysis or regression. Check that variable, get to know it, because you can't analyze what you don't know. Try untested commands on maybe a sandbox or play data set first. Use good labeling on variables and values. Okay, so that's going to wrap up this lecture. We're going to come back to these good practices, and I build them into the labs so you don't forget. But hopefully this helped you think about how to handle data, and we'll see you next time.